This is Algebra 2 with Trig, Unit 1A.2. We're talking about solving absolute value equations. We're going to start out with graphing y equals -2, absolute value of x plus 1 plus 5. So we've talked about how in our standard form the h value is always going to be opposite of what the equation looks like. So this would be x minus a -1, which would show an x plus 1. If h was -1 here, you would have minus a -1. So it shows x plus 1. So the h is -1, the k is 5. That's going to be our vertex. -1, 5. So on your quiz, you might have the opportunity to write down what is the vertex. And that's how you figure out your vertex from the equation. The a value is of course the first term, the -2. We've already done the h and the k. So we're going to come over to the left one and up 5. So that is our vertex. That's where your two lines are going to meet to make the V. Because the a value is less than 1, you know that the V shape is going to open downwards. It's going to open downwards more narrow than a parent graph would be. So we're coming down to and over 1. Because this a value is -2, we can write it as a fraction. So -2 over 1, down 2 over 1, all the way through. And then we have to make the other side of the V shape down to backwards 1, all the way through. And we have our V shape. So connect those dots together. This makes our function, and it's great if you write the equation. -2 times the absolute value, x plus 1 plus 5. Now we're also going to graph y equals 3. Where is y3? Y is 3 across this whole horizontal line. We can grab a different color if you wish, if you've got it. Don't have to. And you come through a different color because it's a different equation. And then that would be y equals 3. And for a solution is where those two graphs cross each other. So we look to see where those two graphs are crossing, 100% crossing. So we know that the absolute value graph is going to exist here at 0 for x, so it's on the y-axis, up 3. And of course, that's also on the green line at 3. So when x is 0, we're at 3. We can also get a solution when x is -2. We're right on y is 3. So the question is, when is this absolute value equal to 3? That's what this system is essentially trying to find. And when we do a system, we have two answers, because this is, you can kind of consider that two-dimensional. We have an x dimension and a y dimension, right and left and up and down. So we have an x and a y as an answer for both situations where they happen to cross. So next we're going to slide down and solve this same problem algebraically. Sometimes graphing is not a great solution. If the intersection doesn't come out as a perfect whole number, then algebraically it's going to work a lot better. So the first thing we want to do is isolate our absolute value. Absolute value is the values inside the bars. We want to get that all by itself. So we're going to move the 5 over to the other side. Okay, what else is with the absolute value bars? The -2, and that's got to move over. We would never want to distribute that into our absolute values. We would divide by -2, and that's going to give us the absolute value of x plus 1 is going to equal +1. So now we've gotten the absolute value portion all by itself. That's called isolating. So now to understand what to do and to do it are two different things. Some people don't understand it and they just do this next part. Then they forget about it later on. So let's talk about it for a moment and see if you can understand why we do our next step. This is an absolute value. And this absolute value is going to equal 1. So what must be inside this absolute value? Not what's the value of x, but what's inside the absolute value for it to equal 1. It could be a -1 inside this absolute value. If that was a total result inside that absolute value, if that was -1, then when we take the absolute value of it, we would still get 1. So we're going to say x plus 1. We want to know when that inside the absolute value is going to equal -1. What else could be inside the absolute value bars? When you take the absolute value of something, we get 1. What situations can we take the absolute value of and still get 1? Take the absolute value of -1, we get 1. Or if we take the absolute value of 0 is always going to be 0. One. So we can do x plus 1, and that's going to be 1. So we weren't looking for the x value, which may have been where you were coming from. So we solve this, and we get x equals 0. That is the value of x for what makes the inside equal to 1. Then we'll have a second equation, a second answer, a second solution. When we subtract the 1, we get x equals -2. So we have two possible values of x that we can plug into this equation that is going to produce a 3. And if you're confused by that, how could there possibly be two answers? You come on over and you look at the graph we just did. There's your absolute value. There's the value of 3. There's two different spots where x is that is giving you a value of 3. And those two values were also found here. When x was 0, we would have 3. And when x was -2, we would have 3. That was the same idea that we had in our solutions for the graph. So what some people think of is I move my absolute value, I get it all by itself, and then I just write whatever this is as a plus and minus. But I want to be sure that you understand why it's a plus or minus. It's because what's inside is actually going to be a +1, or what's inside is going to be a -1, and that's what gives us this 1 to begin with. But long story short, you just get your absolute value by itself and then switch the 1 to be a positive and a negative, because what's inside may have been a positive or it could have been a -1. Let's come on over here and think about this one. What are you going to do here? Yeah. We're first going to move the 3 over. We want to isolate the absolute value. So we have 2x minus 9, that's still in absolute value bars, is going to equal 15. Then from here, is the absolute value written by itself already? Yes, it is. So we're looking for one value in here. When is in here going to be a positive 15? Because I know the absolute value of 15 is 15. So when is the inside going to be 15? So we're going to do a calculation and help us figure that out. Then I'm also going to do a calculation. When is the inside going to be a negative 15? Because we know the absolute value of negative 15 is also 15. So 2x minus 9, when is it going to be negative 15? Because what's inside the absolute value could be a positive or a negative. Now it's just the math. Now we add 9. Here's the algebra. 2x equals 24. Divide by the 2. We're showing our work. And we get the answer of 12. So 12 is one of our solutions. If we plug 12 back in here, we get 24. 24 minus 9 is 15, plus 3 is 18. So that worked out great. And here we add 9, just like we did before. It gives us 2x equals negative 6. Because the 15 is negative, it's larger than the 9. You know the final answer is going to be negative. And then negative 15 plus 9 gives us negative 6. We divide by the 2, and we get the answer of negative 3, because 2 goes into 6 3 times. So those are our two solutions. Those are good to circle because they're both real solutions. Just like over here, we could circle these. Those are our two solutions. All right, currently we have not done calculator work. So when this refers to, it is possible to use your calculator to graph out the absolute value and to graph out what you're trying to make it equal, and you could see where they cross. That would be a possibility. We've talked about how to graph it by hand and how to solve it by hand. So your quiz would relate to just that. Next, we're going to look at extraneous solutions. What is an extraneous solution? And it talks about it here. It occurs when solving some equations. A solution that is not valid when tested back into the original equation is considered an extraneous solution. So you've done all the math correctly, but when you check your answer, it doesn't seem to work. That's called an extraneous solution. You check your answer back in, and it doesn't make the original problem work. So we notice here the absolute value portion is isolated. It's all by itself. There's nothing extra to add, nothing to divide. It's all set. So we're going to take our 15 plus m, and we're going to equal it to exactly what's there. That would be considered the positive version. We're not going to change it at all. So you equal it to exactly what's there. Even if it's negative, you treat it to exactly what's there, and then you're going to treat it to be the opposite. We're going to solve it with a positive, essentially, negative 2x plus 3, and we're going to do it with the opposite of negative 2m plus 3, just like we had done before. So here we go. We add our 2m across because I like to keep the m's positive. That gives us 3m. Then we'll minus our 15. That gives us negative 12. And when we divide by 3, we clearly get x equals negative 4. And hopefully you're moving on, you're working through the other problem. You're not just waiting to copy me. Now, how are you going to deal with this negative? You're going to distribute through the negative and have 15 plus m to equal 2m minus 3. I like to subtract the m's in a way that keeps the m's positive. I don't like to have that negative leading coefficient, so when it's possible, I like to keep it positive. And I'm going to add my 3 to the other side, and that's going to give me 18. So now I have two answers. I kind of expected two answers, and I have two answers. So let's check these answers. Because we have m on both sides of the equal sign, there could be a concern. There are two different m's in the problem. We could have an extraneous solution. We weren't too concerned about that earlier because we didn't have m's on both sides or x's. So when we plug in -4, we have 15 plus our -4 in the absolute value bars. Well, that's the same thing as 15 minus 4, so that gives us the answer of 11. On this side, we'd have -2 times -4. We know that that's a value of 8 plus 3, and that's going to give us 11. So that checked out just fine. When we plugged in our -4, we got 11 on one side. We also got 11 on the other side. It was balanced when we used -4. A lot of times, it's the negative answer that's going to be the extraneous solution. A lot of times. So let's come on over here. Let's try the 18. When we plug in the 18, we get 15 plus 18. That's 33. And that's in the absolute value bars. And when we come to this side, we get -2 times 18. Well, that's -36 plus 3. That's -33. The absolute value of 33 is not equal to -33. So notice how they're not the same on both sides of the equal sign. So this one is not a solution. So we put an X through it, and we write the term extraneous solution. Let's do the flip side. If we were writing the previous problem as a system of equations, we would have our absolute value that was the 15 plus m, absolute value of 15 plus m, and then we would want a second equation as -2m plus 3. That would have been what the system would look like. Then if you were typing this into your calculator and you could get an absolute value to show you a V shape, then you could put in a linear equation and see where the two crossed. We haven't done a ton of that, so we'll let that rest of that slide. But you would be welcome to try that. Come up and see me if you have questions. Okay, these are two you try questions. Just to be sure that we have a chance, if you would like to pause the video, you can work through the problem, and then you'll see that I'll work through it also. So we're going to start out with 4x plus 10, and that's going to equal 6x, and 4x plus 10, that's going to equal -6x. We do the positive version just like it's written, and we do the opposite version with the negative sign in front of it. And from here, that's a quick little solve, and we get the value of 5. And when we plug 5 in, we get 20 plus 10 is 30. Square root of 30 is 30. Or, sorry, the absolute value of 30 is 30. And when we plug in 5, we get 6 times 5 is 30, and that worked out great. Here, if I brought my 6x over, then I'm going to have nothing left on the other side. I would have to subtract my 10 to the other side, and that would give me negative 1. And when I plug in negative 1, I'm going to get 4 times negative 1. That's negative 4 plus 10. That gives me 6. But when I plug the negative 1 to this side, I get negative 6. So 6 and negative 6, not the same thing. So this is your extraneous solution. A lot of times it's the positive answer, like I said. And then to solve the final question, we'll come on down. Of course, we would subtract 5. That's 2. Absolute value of x minus 4 equals negative 4. And we would, that shows us a concern already, but usually we identify it here. We know that the absolute value is always going to be a positive result. So if here we see that we get an absolute value that equals a negative, we see that there's no real solution. This isn't going to happen. This absolute value is never going to touch this spot. Using our graphing calculator, if I was to show you with that, if you hit y equals and math, or we could say 5 plus if you like to. Let's see. Let's go down here. Absolute value is over at number. First I hit math key. Then I slid over to number, so I use my arrow. I go to number, so that's where the absolute value is at, and hit enter. And that is x minus 4. If I want to graph that, I just hit the graph, and you're going to see the V shape, where x minus 4 for the absolute values over here. Notice it never touches negative 2. We can even type in negative 2, and you'll see that it never touches it. So that's why there's no real solution. You could even come up here and type in the original equation if you would like. Math over to absolute value and do x minus 4. And then we want to see that second equation be a 1. And I presume that that's not going to cross at 1. There's no real solution either way you look at it. Now what happens if we do this algebraically? What if we say x minus 4 equals negative 2? Solve this. And I do x minus 4 equals the opposite of negative 2. So I get 2 answers. When I plug them into the original problem, 5 plus 2 times 2 minus 4, 5 plus 2, negative 2, 5 plus 2 times 2, that's going to be 5 plus 4, and that equals 9. That did not equal 1. This needed to be a minus 4 to get down to 1, which it wasn't. The absolute value took care of that negative, and we never got it to go quite where we needed it to. Let's try the 6. When we plug in the 6, 6 minus 4, And we get 5 plus 2, absolute value of 2 is 2. So that gives us the 4 again, which is 9. It needed to be 1. So if this was a 9, yeah, it would work out great. These would be the two answers. But if we have a 1 there, it did not work. So neither answer is correct. No real solution. We typically would not consider that extraneous. It would be considered no real solution because there are no answers that are working.